This will probably be rather intense. I have a lot of stuff that I want to cover. It might be a little bit fast. I'll try to make it as accessible as possible. You should definitely make sure to read the respective chapters in the book, because like everything I say here, you will need a little bit of time to have it sink in. I'll come back to these topics when we talk about examples and we talk about visualization techniques, but I think it's important that we cover this now. Okay, so we started with interaction last time, and the first question that we asked ourselves was, why do we interact with visualization? Well, the main reason is, of course, that we want to be able to explore data that is big and complex. For example, it's too big to show everything at once, or we also want to be able to explore data with different representations. So like the too big at once could be like a map of the whole world and you can zoom in. Obviously I can't show every single detail of the surface of the Earth as it's captured by a map at the same time. But I also can say like there's different visual encodings, different idioms have different fit well for certain tasks. So sometimes it's just good to look at the same data sets with different representations. And then also interaction amplifies cognition. So we tend to understand things better if we can play around with them, if we can touch them, if we can see cause and effect if we do something. So we had this classification of types of interaction. In a single view we have this change over time, navigation, semantic zooming, filtering and querying, focus and context. So we talked a little bit about those two. We'll continue and I'll quickly recap what we talked about here, and then we will continue on to these ones. And the multiple views part here is part of the next slide deck, which will also be covered today. So we have selection, details on demand, linking and brushing, and adapting representations there. And so you can think of multiple views as like it's completely separate research, or let's say it's completely separate entity, but they are also relevant for interaction, and these are just the interactions that you mainly do within multiple coordinated views. So the focus of the second part of the lecture will be on views, and I will also be talking about the interaction in multiple views. Okay, so we started talking about change over time, and I gave you guys this example where I really took time literally. So for example, using a slider to see views with different data at different times. And I also mentioned that sometimes it's better to show these kind of changes explicitly, but it doesn't have to be literal. So change over time, maybe that wasn't quite clear last time when I talked about this. It's also meant to be covering things like changing representations as you go as part of an analysis process. So I'll give you one example here. So like we've seen this visualization before, but what I haven't shown you before is like here we have a stacked bar. And now this stacked bar essentially tells us clearly which is the overall highest value, given all of those together, but it also tells us something about the individual values here. So in this case we can judge like, okay, academic reputation is very high, and then employer reputation is very high, and so on. But down here, like we have this problem of the stacked bars. It's not as easy to compare those two here, for example. If you can see that, yeah. Like to compare those two, well, you can tell that this one is probably smaller, but since they're not aligned, it's harder to compare them. So I could simply change the representation. So instead of having them stacked, I could simply change them to be aligned. And now this is a different task. So the first task was about comparing overall sums, and in this case, it's about comparing these individual values in the columns. And now I can quickly spot where are the outliers that are a little bit lower than the others in this case. Or I could do like another transition here. In this case, I have changed the ordering from this ordering as it is up here to the ordering of the highest value. So you can see that there is some, like in this case, the faculty-student ratio is higher than citations per faculty in terms of its value. So now I don't have the spatial encoding of the association of the bars to what they mean. I only have color anymore, but it also tells me like what are the most important things, and I show them first. So I can switch between those dynamically. And so and what I can also do in this representation is like a hybrid thing. Like if I, for example, click here, I could double click here. I still have like an idea of the overall size of it, but in this case I have aligned it here, so you can quickly see differences both in the faculty-student ratio and in the citations per faculty. So what I'm doing here is I'm changing the representations over time to be able to answer specific questions that I have to adapt to the various tasks. Okay, and as you have seen, we have these animated transitions in here. Well, obviously for transitions in general, we have different representations that support different tasks. So we have seen this example, bar chart versus stack charts. We have seen the change in ordering. And like animated transition make it possible for users to track what is going on. And there's two more examples that I wanted to show you. This is a technique by Ben Fry, who is the author of processing. And he now has its own company that does visualization for hire, essentially. So if you have, if you're a company like General Electric, for example, goes to him and asks him to do installations and visualizations and so on. He was a member of the MIT Media Lab, and he also worked a lot in biology visualization. So this is a biology visualization technique. I'm not going to go into the details what it represents, but it's simply just you see these ribbons that show connections between those various items, and here we have like a genomic scale distance along the chromosome in kilobases, and then I can switch to these various views here. So like I have 2D, and then I have 2D with even spacing, so that what kind of like the in-between area here is equaled out. Then we have 2D quantitative. Then we have a 3D representation where an additional data variable is encoded here. Then I have like another data mapping of this, and then I have the third final mapping. So I don't really want to go into the details about the data here, but it's just like you start with something very simple, and then you can keep changing it slightly to answer different questions. And that's why this visualization is also interesting for that purpose. And the second one I wanted to show you is one of mine, actually. So we will be talking a little bit more about this at the end of the class when we talk about set visualization. But this is about, in this case, movie genres. So you can see that the columns here correspond to movie genres. And like these bars here tell you there are 66 movies that are in the adventure genre. And here this bar tells you there's 101 movies that are both in action and adventure genre, and so on. So what this exactly does isn't that important for this purpose here, but what I wanted to show here is the ordering and interaction. So this is like a query-based interface. So I could say, show me the biggest intersection. Or I could show me the one that has the largest deviation from an expected value. Or I could show me all the action first. Or I could show me all the children's movie first. Or I could sort by degree. Or I could sort by, well, cardinality, we already did this. So like these dynamic interactions, they essentially allow you to answer different questions. And so by picking the right ordering, sorting, hence you're kind of influencing your spatial encoding, you can answer the specific questions. And of course, as a designer, if you know exactly this one single question needs to be answered from your visualization technique, you don't need that. But typically, you have a data set and you want to show it through as many facets as possible. Animated transitions are really about smooth interpolation between states or visualization techniques. So here, the one I just showed you was also a D3 example, but here is a more basic D3 example where you can switch between stacked bars and grouped bars. And if you want to do something like this, here's the code. This is a block from my postdoc. And there's another example for a radial layout, a sunburst, and I can click one of those nodes and it will actually animate, and it will show me kind of like the animation makes it clear what I actually did to some extent. So, and there's another example here. This is a video, and this is a little bit more advanced interaction technique. So I've shown you this before in the introduction, but now I've selected one of the elements down here, and it pops out and shows me the details of that. And the animation actually helps me understand what is going on. So you see the wedge comes out first, and then the angle increases. So the idea behind that is that you are able to see or to understand what is going on. If I were to do this like a rapid switch, without animation, everybody would simply be confused. There's papers on animated transitions. So why do we do animated transitions? For example, this one by Hare and Robertson, and they also have a nice introductory video, and they have a system that shows you this, and they kind of also did research on how well do people understand these animated transition compared to like static or hard cuts, and they also introduced they also researched staggered transitions. So like I don't really have a great example now, but you'll see it in the video.
When analyzing or presenting information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentages, transition to a scatter plot to look for correlations between two variables, or drill down by breaking up the data by categories. Animation is one promising approach for facilitating perception of changes when transitioning between data graphics. Using design guidelines motivated by research of human perception, we have developed Dynaviz, a system supporting animated transitions for statistical data graphics. Dynaviz provides animations for a number of different transition types, including changes of perspective, filtering operations, and viewing changes of data over time. In some cases, changes of value require changing the axis scales. Here we show a sorting operation. Animating everything at once can result in items occluding each other. By slightly staggering the movement of each of the bars, Dynaviz makes the sort easier to follow. Here, a bar chart becomes a radial donut chart. By growing the wedges to take up the whole circle, we form a pie chart. We can also perform drill down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a grouped bar chart. Of course, we can always reverse the transitions to return to the view we started with. We might want to compare different variables in a scatter plot to look for correlations. Here, we keep the y-axis values as the same as the bar chart, but use the x-axis to show a new variable. Animation is also helpful for showing transformations to the data. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the transform. Visual encoding such as shape, color, and size can be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran two controlled experiments. The first experiment asked users to follow two targets across an animated transition and click their final positions. To better test how animation affects memory, we masked the display after the transition by turning it black. We compared static transitions, direct transitions in which all items animate at once, and staged animations where movements were split up over time. Our results found significant benefits for animation and found that staged animations, which split up movements through staggering or separate stages, consistently improved accuracy.
So, it's clearly correct that animation is better than not animation in this case. There have been follow-up research studies on this, on staged animation. The paper was actually titled "The Not So Staggering Effect of Staggered Animation." And it talked about that the staggered animation doesn't really help too much in many cases. And if you look closely here, the differences between the staggered animation, or staged animation as they call it, and regular animation are pretty small. So the guideline is try to do animated transitions. Staggered are nice, they are a visual effect, you probably don't have a big cost, but they are not extremely helpful. One thing you have to be careful about though is if you have a lot of data, let's say I'm adding a couple of more of these elements here, and now I actually have, you can see way more stuff than there is on the screen. And in this case, animation becomes a little bit overwhelming. So there's not much you can follow here anymore because there's so much going on. And yeah, there can be more extreme examples. And so what we did here, for example, we kind of defined an upper limit, and at a certain point we simply don't show the transitions anymore. Because A, it's hard to follow, it doesn't have a lot of benefit anymore, and B, it gets a little bit expensive from a computational side of, from a computational standpoint, because this gets really slow if we have even more elements here. So like, let's say I'm adding more and more data values, and now, like you see, this is really long already. And let's see, yeah. So you can see this is kind of, we have passed the threshold for animation at this point. We have set this arbitrarily, but we found that it's both not helpful from a user's perspective and also makes simply the system more responsive. So there's a limit to what you can do with animation, but it's still, if you have like a limited number of points, it's pretty good. Okay. So, any questions about animated transitions before we move on? Good. So we talked about navigation. I gave those two examples about panning and zooming and rotating. I'm not going to show them again. This is the theory behind this, the space scale diagram. So where you have essentially a viewing window that you essentially move with respect to a camera or to a scene. So by moving it further in, you kind of see a larger clipping of a scene, and by moving it around here, like by moving it around, you execute the panning operation. So this is an important paper that kind of conceptualized this, but it's kind of natural, the panning and zooming and rotating operations. We had this example. One thing to note, maybe, is that in 3D navigation, you sometimes also have restricted navigation. So completely, fully free 3D navigation is tough for people. If you look at people who work with computer-aided design, developing 3D models, they usually have specific input devices, which are called a space mouse, so that they can actually easily rotate things and so on. In visualization, it's often helpful to have a couple of predefined perspectives, so that you don't allow people to the complete freedom of moving around, but that you pick the viewpoints and let people transition between them. Okay, so this is where we stopped last time. So in contrast to regular zooming, there's also a concept that is called semantic zooming. And here's an example that if you have a Windows computer, you're probably familiar with, but you probably didn't know that it's called like that.
Hello, my name is Adam Barlow. I'm a program manager on the Windows Developer Experience team. Today I would like to introduce you to the semantic zoom control, which is included as part of the Windows library for JavaScript. Semantic zoom is a control used by apps in Windows 8 for displaying large sets of content in a truly user-friendly format. Semantic zoom is unique in that it provides an easy-to-navigate, touch-optimized view of the data you present to users. In designing Windows 8, we wanted to ensure users wouldn't have to pan tediously through large sets of content with touch. Semantic zoom is our solution to this problem. It gives users the capability of quickly jumping to sections of the view and greatly reduces some of the pain points traditionally associated with large collections. As you can see here, semantic zoom allows the user to quickly jump to any given location in the view, in this case, the last group of my start screen. Not only is semantic zoom a great navigation mechanism, but it also allows you to communicate a higher level organization to your data, using the zoomed out or semantic view. For example, in the People app, you can zoom out. Here you will see a higher level abstraction of the data in terms of letters of the alphabet. This is extremely powerful and can be used to communicate important information to the users of your application. For instance, you can use the cell-spanning functionality of the WinJS list view to demonstrate the relative sizes of your groups. Although semantic zoom is easily performed with touch using the pinch and stretch gestures, it also works well with mouse and keyboard, ensuring that regardless of input mechanism, your users will have access to the important benefits of both the jumping and presentation functionality. With mouse, you can use the semantic zoom button located conveniently at the bottom right of the view, and with keyboard, you can zoom by holding down the control key and pressing the plus or minus keys on the keyboard. There are many app scenarios which would benefit from the inclusion of semantic zoom. Content organized by alphabet, as shown in the People app, and even disparate group content, such as the Travel app, all benefit from the functionality it brings. You may be asking, great, but when should I use it? A good rule of thumb is, whenever your view becomes sufficiently complex.
Okay, so the idea of semantic zooming is that you have a representation, and as you zoom out, you don't show every single detail, but you kind of make it more simple, and as you zoom in, you show additional information about it. Windows has adapted this now, but of course this idea has been around for a while, so here's a...
LiveRack, interactive visual exploration of system management time series data. We show LiveRack, a visualization system for viewing large quantities of time series data in the domain of system management. Monitored devices are represented by rows. This label shows aggregated information about a group, NFS, with 4 devices. Columns show one or many parameters collected from the devices. This column shows CPU usage. In the current overview, each cell is a small colored block. In these 4 cells, green means CPU utilization is above 35%. As I make the cells larger, labels for the individual devices become visible. Also, when the cells get big enough, the server is queried for more data, and then the representation changes from blocks to spark lines. Making a cell even bigger results in semantic zooming to show a more detailed line graph. We can see the current time range by looking at the time boxes to the bottom left and bottom right of the data area. The blue lines show progressive search results. I'm searching on NFS to flag the devices I've already stretched out.
So the point I really wanted to make is this aspect here, that as you zoom in, you actually are supplemented first with just a spark line, so like a very simple line graph without axis. And if you zoom in further, you get axes, labels, text, and so on. Yeah, and so the idea behind semantic zooming is, of course, that you make it meaningful at multiple levels of resolution. So, like, you would have some representation that works if you zoom out, and you have some additional informative representation that works if you zoom in. Okay, so let's move on to focus and context. And focus and context is a super popular general principle, and you will see a lot of papers about focus and context. So focus and context is about carefully picking what you show and hint at what you're not showing. So the idea is that there is some part of the data that is in your focus that users want to see in detail, but it's also important to show some of the contextual information so that they can orient themselves. So focus and context is really a synthesis of visual encoding and interaction. So like we have the part that is how it is represented, the details and how the overview is represented, and how I change the focus continuously through interaction. So the user selects a region of interest, which is called a focus, through either navigation or selections, and then you provide, as a visualization designer, aggregation, reduction, or layering. So this is like the classifications of focus and context techniques. It's called a little bit different. It's called embed in the book. So you have eliding data, superimposing layers on top of it, or distorting geometry. And we'll go through those now. So elision is you show one focus item in detail and you summarize other items for context. And so if you look at the word elision, what it means by the classical dictionary definition, typically it's used as the omission of a sound or syllable when speaking, such as in I'm or let's, or the process of joining together or merging things, especially abstract ideas. So the idea is really here that you bring two different things together and omit something in between. Here is an example for the space, that is called the space tree. So you have, this is essentially a hierarchical navigation system. So you have like a root here in the tree, and once you click an element, dynamically the children of it are popped out and the position is changed. So you have, the focus is what you're currently looking at, and the context is the way back to the root of the tree in this case. More generally speaking, and this is an important concept in visualization, is a degree of interest function. So a degree of interest function works that we have, as humans, if you think about your lives, or like if you think about your neighborhood, you're pretty familiar with every single house in your neighborhood, but for everything that is further away, you kind of know major waypoints, but you don't know all the details, of course. So the goal is to balance a local detail and a global context. And so there's Guy Furness in 86 or even 82, the first paper on this was in 82, came up with this function that defines the degree of interest of an item X. This could be a node in a tree, for example. And so you have two functions here. You have an a priori interest of a function and the distance function to the current focus. So it assumes that I have, for example, in a tree, that I have a tree each of these nodes has some a priori point of interest, and usually the root of the tree is, for example, very high, but it can also be data driven. So you could say this is a really important person, this is a really important person, but this one not so much. And so the degree of interest function has this a priori information. So you could say this is 3, this is 2, this is 1, this is 0, 0, 0, 0. But then the second part of it is this distance function. So when you select one of those nodes, this obviously is the most important thing. And then all of the other ones are computed, or the relevance of all of the other nodes are computed based on this function. So this one here probably won't be very important because it's far removed from this point, so you might actually not want to show it. So you can essentially assign a weight to each of these elements. This is a very general concept, so the tree is just one example that's easy to understand. But here is a technique that uses this. This is a degree of interest tree. I'll just show you the video. So you can see that as we navigate through the tree, it's not that direct children pop up. It's more that there is some a priori interest for these elements. So if you click here on, in this case, oh, it's hard to read. Well, it's not that important that we actually read it, but you can see that things are aggregated here. And if you click on a detail, it's not directly its descendants or its parents are popped up, but other things that are relevant to it or other things that are relevant in a global context are popped up. Yeah, sorry for the blurry video. Okay, the next concept in focus and context is superimposition. So you have one focus layer that is limited to a local region of a view, and instead of that stretching across the entire view. And the typical example for that is a very traditional or very historically interesting technique, which is called magic lenses. So this video here that I'll show you in a second is from a 1993 video on tool glass and magic lenses. Tool glass is a cool tool, but this is more interesting for ACI. Magic lenses is about visualization. And so the idea of magic lenses is that details or different data is shown when moving a lens over a scene. So you have like a virtual lens, and then you would show like a different representation. So you can see that in this video. We'll first start with tool glass.
Current interfaces often require users to switch their attention between two types of screen areas. Work areas, in which information is displayed, and control panels containing buttons, menus, and other interactors. Our new interface reduces this effort by taking better advantage of three common skills. The ability to use two hands in concert, as when playing the piano, threading a needle, or typing. The ability to bring tools to our work, as when drafting, driving a nail, or choosing a paint color, and the ability to enhance our view, as when using a magnifying lens to view small objects. You are looking at the screen of the Sun Microsystems SparkStation 10, running the Cedar programming environment. The SparkStation is equipped with a mouse for the user's dominant hand and a trackball plus thumb wheel for the user's other hand. This region of the screen contains a simple window system that we will use to demonstrate two new user interface techniques, tool glass and magic lenses. Tool glass is a movable, transparent control panel that appears above application windows. We can move a sheet of tool glass in two ways, by dragging it with the mouse or with the trackball. Using both input devices, we can move a tool glass sheet and the mouse cursor simultaneously. A transparent control panel enables new kinds of user interface tools. For example, this color palette is a set of buttons called click-through buttons. Clicking through one of these buttons changes the fill color of the object beneath. These buttons work over several applications, including a graphics editor, a rectangle editor, and a text editor. Tool glass requires only core.
Okay, so the idea of the tool class, if that wasn't clear, is that instead of having a menu bar on the side where you would pick a color, you move around your menu bar and click through it. But the more interesting part of this video is the magic lens, at least for our purposes.
Control the magnification with this slider, appearance of the object. Tool glass sheets can include magic lenses, visual filters that modify the appearance of the objects beneath them. For example, this lens magnifies the objects underneath. We control the magnification with this slider, increasing or decreasing. This second lens is a filter that shows only red objects.
That is actually a magic lens, so if you just
Overlapping the
magnify
two
it,
filters composes their effects. When we place the magnifier lens over the red object lens, we see that this little red object is a Time magazine. Magic lenses can be used to modify a scene's appearance in small regions while leaving the rest of the scene alone as content.
Okay, so there's this is the original video, and people have taken this idea very far. An interesting side note is, I think this was in '93, which is way before Windows 95 and so on. This was at Xerox PARC, and PARC Lab at this time was really very advanced with all of the user interfaces and HCI research. Here is an example of a magic lens with a tangible interface. So tangible interfaces are usually something that you can touch, and they used often in combination with a tabletop display. So here you have two different things. You have a tabletop display, and then you have a sheet, and you move the sheet around, and depending on where you are over this table, this visualization here is altered. So in this case, you see there's just the outline of a body, but the sheet draws, like on top of the sheet, more information about the muscles of this body is projected.
In this video, the User Interface and Software Engineering group at the University of Magdeburg, Germany is demonstrating a set of novel navigation techniques for exploring information spaces by using tangible magic lenses in a tabletop environment. Up to now, tabletop interaction is often limited to the two-dimensional surface. In this example, users can zoom and pan through large pictures by performing multi-touch gestures on the table surface. In the following, we show how this task can be accomplished in a more natural way. For this purpose, we developed a paper-based mobile display that users can freely move through the physical space above the tabletop. This magic lens works as a magnifying glass to zoom in on an image by simply lifting or lowering the lens. At the same time, moving the display horizontally results in a panning operation. In order to help users maintaining the context, a circular contour line is projected onto the table display. The technical setup of our system is simple. The images on the lens display are generated by a projector and an infrared camera above the table. It works because the mobile lens contains markers in the corners that reflect infrared light. So the infrared camera above is able to track the lens movements. This tracking information is then fed to a computer which tells the projector what image to display on the lens. We have also applied the mobile lens concept to other types of information spaces. The layered information space is a set of two-dimensional data, with each data layer representing a unique feature of a contextual model. In our example, medical students can study different systems of the human body. By lifting or lowering the lens, they can choose between the skeletal, muscular, blood, and nervous system.
Okay, so you can do this, like this projection setups and so on, they're a little bit static, but now you can also do this with smartphones or tablet devices. And how you do that typically is that the tablet devices film the underlying scene and therefore know where you are and therefore can update the content. So you don't need like this camera set up with markers and so on anymore. There are also other types of magic lenses. For example, you could use these for labeling. This is a circular labeling lens here. So like you would be moving around this circle on a scatter plot, and around this circle you would see the labels of these points. Or you could use a magic lens in graphs, for example. So here would be a lens on Toronto, and you could see that the edges bend around it so that you can actually see what is going on in here. So these magic lenses, they have many purposes, many uses, and they're researched a lot, and they're often researched in context of physical spaces. So augmented reality visualization, so you want to see through a body or something like that, especially. So I guess the interesting part for magic lenses is really when you can't alter your spatial representation, so if you have inherently spatial data. A completely different, or well, conceptually different idea is distortion. So that you use geometric distortion of contextual regions to make room for details in the focus regions. So here's one example, which is this, one of the very first InfoVis papers, that was dedicated information visualization papers, the perspective wall. So you would have this is files in a file system that are split along, or are positioned along this axis here, depending on when they were last modified. And the idea is here that this would be a very long timeline. So instead of showing you all of the details or an overview of everything, they choose to use geometric distortion for focus region and context region. So you see like the front of the wall in detail, and then you get an idea of how many files are there at the sides. This is interesting.
The perspective wall is used to lay out 2D information onto a 3D segmented wall. The front segment is used for viewing details, and the side segments provide context. In this case, each node represents a file with its horizontal position determined by its date of last modification. Vertical position is used to indicate the class of the file. When a node is selected, the wall moves to bring the selected node to the center of the front section. As before, we have a fisheye view. We're using 3D to make better use of available screen space.
Okay, I guess you get the idea. General application of these are fisheye views. So here you would have a lens that you could move around in the interest of time, but you could easily imagine how that works, and we've seen this. So you would have a lens moving around, and you do some geometric distortion locally, and you can see this as the grid. This is the function of the magnifying factor here. This was like a big deal, and people were super excited about it. I'll give a little bit of a comment on that a little later. And then we have the hyperbolic trees. So the idea here is that you have a tree that is projected onto a hyperbolic surface or on a sphere, and that this kind of gives you a natural way of moving around in this space. So you would have, like by moving around this sphere, you would see the objects in detail, but the contextual elements kind of disappear behind the edges of the sphere, and you only see the little the branches going out. And as you move around, you see more details. This was another Xerox PARC project.
The hyperbolic tree browser is a focus plus context technique for browsing large hierarchies. Here we see a recent org chart of Xerox PARC containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as nodes approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail in that part of the org chart while maintaining the context of the whole. We can also grab a point in the space and drag it around as we like. To achieve crisp dragging and to keep transitions under 1 second, rendering of the tree is degraded in a couple of ways. Notice that the arcs are turned into straight lines and less of the exponential fringe is painted.
So the technical details are not relevant in 2015. Yeah, but this was a big deal, and is a big deal. This was actually patented, and they sold this part of an InfoVis toolkit for a long time. So you can't really use it exactly as they did. You can do these lenses, of course, on maps. So here is a little video. Yeah, so I guess you get the idea. And then you could, of course, do this also, like this is a more recent technique with
It is possible to
good
monitor
rendering.
the activity of buses throughout Singapore, but considering the large volume of information, exploring individual bus stops is a challenge for visualization. In order to achieve this, an interactive tool has been developed. It acts like a magnifying glass, allowing you to explore with great detail the activity of the bus network in Singapore. This magnifying glass distorts points in space to accommodate great zoom levels. It permits local browsing of the space, maintaining its continuity and emphasizing other distinctive points in the periphery. The lens can be dragged over the bus network of Singapore.
So, yeah, all of these things look really cool, and they're a lot of fun to play around with. They have they're somewhat dangerous. So I also wanted to show you, we of course have done something like that too. So here in this case, like we also have a very long list. So what we did here is we used the fisheye projection. And so once you click somewhere, you can still, like you see the details of it. And here the distortion isn't too bad, and you still have a pretty good orientation. I'm gonna line it by this, so you still have a pretty good orientation. But yeah, these interfaces, they are a little bit dangerous. Here's another prominent example. For trees. And the idea would be, of course, that you have very large trees that are hard to navigate. And once you zoom out, you can see the structure of the tree, but then you, of course, lose the details. So you could use these lenses to see the details. So here you have the lens and how you can navigate with it. So if you have this kind of linear structure, as we have in this example and in the lineup example, I think they're fairly good. But if you have like these on the maps and so on, as you saw with the Metrobus system, there is a lot of distortion going on around the edges that isn't very clear what is really happening. So the general trend in visualization research is kind of to go away from this. Well, I'll talk about this now and then go back to the slide. So the problem is that this is really not suitable if you have spatial judgment. So if you use position to encode any data, you can't really use the fisheye lens on top of it because you kind of make it unusable because you distort the position, obviously. It's also hard for people to track the distortion, like mentally, and you also have to visually communicate the distortion. So typically people do this with these grid lines that are distorted or with shading. Then you have the targeted acquisition problem. So the lens is displacing elements that are really actually close by. So you see what you are currently looking at in focus, but all of the things that are immediately right next to it are actually shown in the smallest way possible. So that's a little bit of a difficulty. And so the research shows now that we have kind of mixed results compared to separate views and temporal navigation. And even the furnace, the person who did this defined this degree of interest function, He gave fisheyes as an example, but he really didn't mean it to be used mainly for geometric distortion, but he meant it more for like filtering elements out of a display. So he actually thinks it's not a good idea to use this for distortion. So I have been super enthusiastic when I started out in visualization about these distortion techniques because they were just so great and fun to use and interesting to implement. But yeah, recent research kind of shows you that, and if you really want to achieve something with them, they can be sometimes a little tough. Here is a really nice example of the inverse problem. So you have a distorted shape and you straighten it out. So this is called transmorgification. If you guys read Calvin and Hobbes, you know what that means. Essentially, like this Calvin transmorgifies himself into a tiger and into other things. The idea here is that you have non-linear shapes and linearize them. And I really love this technique because it's just so beautifully implemented. So you can do this for not only for pictures, but you can do it for other things, for visualization techniques. So you can take a radial chart and actually make it into a bar chart. And all of this happens in image space, so they really only apply image transformations to that.
Does it play the classy music the whole time you're doing it?
Yeah. Okay, so this brings us to filtering, aka brushing, aka selection, and dynamic querying. And I will only talk about the interaction aspects of that. So we will have a dedicated lecture on filtering and aggregation right after the fall break, but here I'll briefly talk about interaction and filtering. So before we start talking about filtering, I think this is a good point to introduce the mantra in visualization. This is Ben Schneiderman. He is kind of the most cited author. So like if you look at Google Scholar, he is, I think, by 40% more citations than anyone else in the field. He is at the University of Maryland, an HCI and visualization researcher, and he came up with this mantra in '96 that he calls overview first, zoom and filter, then details on demand. So this is kind of like the analysis process of how you should design your interfaces to support this analysis process. So the idea is that you show somebody an overview of all the data, then you let them zoom and filter in on something they identify as interesting, and then you provide the details on demand. And he also, and this is very prominent, and it's a good guideline if you design a visualization system. There's also additional tasks which he calls relate, history, and extract. So relate items to each other, keep a history of others, and extract essentially means define a subset and move it somewhere else. But what stuck with people was this paradigm of overview first, zoom and filter, and details on demand. And he actually has this sentence 10 times right after each other in the paper for every time he rediscovered it when he did a visualization project. So this is a great guideline. You have to take it with a grain of salt, especially in the area of big data. Because if you say, want to do data visualization of the topological structure of the internet, an overview of all of the internet is not going to bring you very far. So you have to be a little bit careful. You have to think about the context. This was in '96, so it's still valid, but you don't like. There is good reasons for deviating from it. Filtering, dynamic queries and filtering. So this is actually also by Schneiderman, and he is actually narrating this video. So filtering, the idea of dynamic querying is to define criteria for inclusion and the exclusion. So you probably all notice for, like, if you're looking for a new television on Amazon, you would simply define, oh, I probably want it to be between 44 or 49 images because my wife doesn't want a bigger one. And then you could define price ranges and when it was built and ratings and so on. So this faceted approach to like redefining user interfaces has become very popular, and it's a very powerful approach to drill down into information. So this kind of originated in HCI research, of course, and visualization research. And here's an example.
Again, the principle is to
This is the same guy that you saw in the picture before, just a couple of years ago.
visually demonstrate the query components and the results and provide rapid and immediate feedback. For that, I'll take a look at the demo here on this display. Just move over to the side here, and we see on it a map of the Washington, D.C. area with the Potomac here. And this is an improved version of where we were a year ago in terms of dynamic home finder. The scenario I present to you is that we're coming up on a new administration, and you've taken a job with the Clinton administration, and your spouse is going to be working at the University of Maryland. You're looking for a home. So the first thing to do is to mark where you want to work here at the University of Maryland, right about, let's say, there, the A marker. And then your spouse is going to work downtown in the executive office building, right about over there. There's the B marker. Okay. And now each of these points of light on the display represent a home for sale. And if I move to the right, I can control this display by choosing the distance that I want to be from point A. And now it's set at 30 miles, and I'm going to bring it down. And you can control rapidly, incrementally, and reversibly the distance that you wish to be from point A. So let's say you decide, you see there's plenty of them, so you say you want to be, let's say, 5 miles from work so that you could, let's say, bike to work. And now you want to be somewhere inside that range from B, so you slide down, and we now can see the set. And this is, looks like we've got 40 or 50 homes over there. If I now choose about the number of bedrooms, I really want 3 or 4 bedrooms, so I move this double box slider to be 3 or 4. I've still got about 30 houses on the display, so why don't we look at the price now, and we want to keep the price down, let's say about 170,000, between 140 and 170,000. And that's given us a set of about
Okay, housing prices have gone up since. But, so 1993. So the idea here is really this sliders kind of control of all the parameters and kind of let you do your selection of the data. We have like here in this case we in the 2 previous examples we had widgets that are outside of the visualization. So we had controls that allowed us to define a parameter. And I've shown this one to you before. I can also do this directly within the visualization. So here I'm actually filtering directly on the axis of these parallel coordinates plots. And so this is why I also had this caveat, so you can call it filtering, highlighting, selecting, and so on. All of these things are just different interpretation of the same one that you divide essentially your items into a set that is included in something and a set that is excluded in something, and then the distinction is only rendering. So here I could simply essentially define filters based on multiple criteria and drill down into these elements, and then now I would have selected 3 different cars. The benefit of doing this like that is, of course, that I don't have to have extra widgets. I don't need to waste space on extra widgets. But, of course, the visualization technique needs to be suitable for that. You can do this with various things. So you can also simply do these rectangular brushes on the space. You can do angular brushes to define angles, and so on. So these visual queries, they're very powerful and they're very common. You can do lasso selections. All of these are possible. You can do this, of course, in spatial data. So here in this case, we have a connectivity graph of the brain. And here we can see that it has been filtered to the path that come in, probably here, from the neck. And here they have been filtered further down. So this doesn't only apply to InfoVis technique, it also equally applies to SciVis techniques. And it's also very equally important in scientific visualization. Another way to filter or query would be incremental text search. So we have seen this example of the baby named Wizard. So I'm putting in men. Oh, sorry for wrong filter. So we can see Manuel, Manuela, Mandy. So every time I simply if I just put in an A, it dynamically filters to everything that is only A. If I add an L, it filters to all of the elements that are an L. So this is a different way of filtering. In this case, it's by text. And then you can do more complex filtering and query operations. And there is like a multitude of those. I'll just show you a simple example in this technique that I showed you before. So here, this is a Simpsons data set. Whether people are in school, have blue hair, like Duff beer, are evil, are male, or work at a power plant. And so I could select, let's say, these are the people that are, where is something interesting? Let's go for evil. The evil males. Or the evil males that work at the power plant. And we would see this as Mr. Burns and Smithers. So what I could do here is, and this is of course pointless because it's a simple example, but I could say I am interested in a subset in all of the elements that are in school, have blue hair, but don't drink Duff beer. So you can see here I get a textual representation of this query, the intersections of said school, blue hair, but excluding said Duff fan. And then I could do logical operations, or like in this case I have added an OR operation to that. So you can do essentially an arbitrarily complex query on that. And once I confirm the query, I get presented with the subset, like all of these elements match that query, and if I select that, I can see which elements that are. These kind of queries, essentially you can do things like complex SQL queries through visual interfaces too. You will see many of those if you look at for visual analytics interfaces. We are now working on one, for example, for graphs, for topological restrictions in graphs, and so on. So these are very important to answer specific questions about data sets. More on filters and aggregation will form a more, let's say, data perspective after the fall break. So this leaves me with 20 minutes to talk about views. Let's see how far we get. Okay, so up to this point we've talked mainly about a single visualization technique. But in fact visualization usually, or visualization systems usually use multiple views. And the idea behind this is eyes over memories, that you trade off display space and working memory. So if we had this time partitioning where I showed two different representations of a data set by choosing to animate between them or by choosing to transition between them, I still have to keep track mentally of what was before, what is now. If I simply add a view with this different representation, I don't have to do this. And This is actually very effective. We're bad at remembering details, and if we see, let's say, a pattern in one view, we might want to be able to relate it to the other view. And if you need to switch back and forth between them, sure, animation can help to track these elements, but it's easier for us to do this if we see both of the views at the same time. And so there's this classification of how you can divide views. So you could have the encoding could be either the same or different. You could have shared data, either all of it is shared, a subset is shared, or no data is shared. So that it's, for example, just a link by item identifiers. You could have shared navigation. And so here is this matrix of approaches, or how this is called, when you vary encoding and data. So you have the same encoding and all data, then it's of course redundant. So you would show the same plot twice. If you have a different encoding but all of the same data, it's called multiform visualization. If you have a subset of the data and the same encoding, this is overview and detail. So I would show, like, I'll give you examples later. If I show different data with a subset of the data, then I would have multiform overview detail. So I would have a different representation for the overview and a different compared to the detail view. And if I have no shared data, the same encoding, it would be small multiples. And then if I have different encoding and no shared data, it's pointless. Yeah, so this is kind of the most important thing. Linked views is really like if I have these multiple views, if I print them, they're next to each other. But if I use them in an interactive system, I can actually help people to understand the relationships between them by linking them. And so multiple views that are simultaneously visible and lined together such that actions in one view affect the other, and particularly filtering and highlighting. So if I highlight one item in one view, it should also show up in the other view. And you've of course done this already in your homework. So for linked view, I have these options like that I went through with encoding and data sets, and then you have the options of highlighting and navigation. So do you link highlighting or not? Do you share navigation or not? So let's go through these examples. One of these principles is multiform, so that you use different visual encodings between the views. And the idea behind that is, of course, that each view has a limits on the number of attributes that can be shown simultaneously. So here is an example that kind of takes this multiform idea to the max. This is actually one of my papers.
VisBreaks is a visualization technique for inhomogeneous data sets. The idea is to split the data into homogeneous subsets and to visualize these subsets individually in bricks. In this example, we compare the gene expression values of different types of mice. We've divided the data into groups, where one group contains all experiments conducted for a mouse.
Maybe I'll skip ahead.
The arches different areas.
So here you can see that we can switch these visual representations.
Dimension group. VisBreaks are a multiform technique. That means that its data can be shown using multiple visualization techniques.
So, and you can switch different representations, and these different representations have different properties. So histogram gives you an overview, and the one view you saw, this is like a very rough guideline. And you can pick and choose which of these parts of a data set you want to see. But where it gets interesting is we can take this partitioning a little bit further. So by clustering these data sets, we would see each of these individual subsets here. So here we have clustered the data set, and we have now different groups. And the idea here is that each of these groups, if you have clustered it, is homogeneous within itself, so I can represent it more efficiently. So you can see here the red means this is high, and the green means this is low. And the little triangle will show you the standard deviations. And I can switch for every of those visualization techniques. I can actually switch the representations dynamically. And I can then show this for multiple views and see the connections between them. And what I can also do is a detailed view. Here I'm actually brushing and have this linking and brushing, colored highlighting. You can see the individual elements. And then finally, if we want to see really details, this comes to the very end, or I can change the size of any of those elements, but I can also pop out a detailed view. So this was really the idea here, was really to take this idea of multi-form and divide and conquer to the max. So when we have shared data, it's about showing all data in each view, but with different encoding schemes. And the idea behind that is, as we had already when we talked about transitions, is that different views support different tasks. So here is an example of Matrix Explorer. This is the same data set on the left and on the right. And in this case, we have a matrix representation, and here we have a node link representation of the same graph. And we'll be talking about these representations. I don't want to go in detail in the lecture on graphs, but just so much to say that the matrix representations, they essentially show you the links here in the matrix, whereas the node link representations show you the links as these lines. And both of them have benefits and drawbacks. So the matrix representation is great for dense graphs, and it's great for visualizing edge attributes, whereas this technique is better, or node link diagrams are better for topology tasks. If you want to see how are two things connected, that's easier to achieve with that one. So the idea would be that you present both of them at the same time, that you link them so that you can make use of both of these techniques. A different concept is overview and detail, where you have one view shows a summarized summarized information about an entire data set, while an additional view shows more detailed information about a subset of the data. And of course, this is again focus and context. Overview and detail, they are kind of related to each other. So the rationale is that for large and complex data, a single view of the entire data set cannot capture the fine details. So here is an example. It's called stacked zooming. It uses the same data, same representation, but just different levels of detail. So you have a line graph. And you have two overplotted line graphs here. And then you can select an area of detail, and it will show this to you in these client views at the bottom here. So you have the green area here and the gray area here. And you can take this to multiple levels. Sometimes, well, I would argue this can get a little confusing at some point, but still the idea is very valid. This is one of Mariah Maya's techniques. It's called MISB, and she's done this detailed view. Like she has an overview. Here in the center, this is essentially evolutionary relationships between two species. This segment here shows the chromosome of one species, and all of these other chromosomes are of another species, and so they're interested in conservation between those parts. And so what she shows here is the overview of everything. It's like you have one species, this is actually the other species in the outer ring, and the selected segment is added here to this inner ring. But what I really wanted to show in this example is the relationship between this view that gives you an overview and this view here that shows you the details. So for here you see chromosome 1 in a very abstract representation, but or in this case now chromosome 4, but here you see it in a very detailed representation. And then again you have these relationships between two selected ones in even more detail. So you have like the global overview plus details on the side of it. And also this shows you of course more data and a different view on things. Another very important techniques are small multiples. So the idea here is that each view uses the same visual encoding but shows a different subset of the data. The rationale for that is that you can quickly compare different parts of a data set, and again relying on eyes instead of memories. So like this is, for example, a very efficient technique to compare attributes of a graph. So here we have one graph that is shown in detail, and these little ones here are actually the same graph. It's exactly the same topology, so all of the edges you see here are repeated all over. The only thing that is different is the color coding. And the color coding is, in each case, for a different experiment. So you can see, like here we have, for example, a red node up here, which is not red here, but it's red here, and so on. So you can define those very flexibly. By dynamically adding the level of aggregation here, you can add more of these small multiples as you go. And small multiples are really a very efficient way of, and of course in combination with this highlighting, you can clearly see, okay, there are clear differences between those elements. And if you, for example, do this by switching against them, you would have 6 different time points that you have to switch to, and that would be pretty challenging. Okay. This is a very simple example of linked highlighting. So you have different views, and if you select something in one view, it's highlighted in the other view. I'm just adding it here for, like, it fits into the structure of the presentation, but we've seen this before very many times. So, like, if you pick one element in one view, you see all of the relationships in the other view, as you have done it already in your homework. You could, of course, also have this with linked navigation. So in this case, we have this tiny miniature view of the world, and we are dragging around this rectangle, and we can see that this larger view updates. And so this was very common in map displays. So until a couple of years ago, you still had it in Google Maps, for example. It became less common, I think, with better connection speeds, where you could simply zoom out and zoom in so rapidly. The only place I see it now commonly are video games, where you have like strategy games, where you World of Warcraft or in Warcraft, where you have a map and then you can like change your viewing window depending on that. But I haven't seen this in recent interfaces. Okay, so partitioning of the data. Partitioning is really, really important for visualization because it allows you to separate the data into groups. And there you have a couple of design choices. Like, how do you divide the data up between the views? You could have a hierarchy of attributes. How many splits do you make? Which order of the splits do you make? Do you decide on? How many views do you use? And these partition attributes are typically categorical, but of course you can transfer any data into a categorical data set. So here we have this. We could show you like all of this as just one bar graph, but it actually was partitioned here by states. And here in this case, it was not only partitioned by states, but also by age. So like now we have here we have one division, and here we have a second division showing the same data, but they show different things. So here you're better at comparing inter-age or across state, whereas here it's really more about like seeing like within the state how does it relate to each other. So like these splits and how you divide them, that is a very important design choice in visualization. Related to that, this is the scatter plot matrix. So a scatter plot matrix takes a multidimensional data set and plots each of the dimensions against each other. Like, I'll give you an interactive example here. This is again D3, you can look at the code. Here we have, this is a classical data set, a classical statistical data set about flowers, how the petal width and the petal length and the sepal width and the sepal length relate to each other. And you see these nice clusters. So here, this would be, this plot would show you sepal length against sepal width. This plot would show you sepal length against petal length, and so on. So any combination here is possible. And you can see these clusters. And of course, this is linked. So I can select an item here and I drag this around and I see the related elements. So we will talk more about scatter plot matrices and what they do and how to navigate them and the downsides and what you do with the duplicates and the symmetry, how you deal with super large scatter plot matrices and so on in the lecture on high dimensional data visualization, the second half of the course. But here this is just like multiple coordinated views here in this case to show you a whole data set. Let me check the time. We have 5 minutes. So trellis plots are similar to, well, they're a way of partitioning data. You have panel variables, you have partitioning variables, and you also have an ordering here. So here is a trellis plot. So what this shows you is the yield of various types of grain in various areas for 2 years. Like here we have 1931, we have 1932, we have areas, Boisseca, University Farm, Morris, and then we have types of grain, or barley in this case. And this is in bushels per acre. So like here this was divided, and it shows you this like as these dot plots. So here again we have split up the data, and we can, and so this is sorted by group median. So you can see that the highest are on top here. And then we could also do this combination. So here we've chosen not to do the split between the 2 elements, but we actually, instead of splitting by year, we're using a different encoding. So this just to show you the options that you have as a visualization designer. Do you choose to divide spatially, or do you choose a different color for a different categorical attribute? And a system that really explored what you can do about this is, or how far you can take this, is Hive, the hierarchical visual expression visualization technique. And this is really about partitioning data based on a hierarchy, and then reconfigure these partitioning hierarchies to explore the data space. And they use tree maps as space-filling rectangular layouts. I think I've mentioned tree maps before. Tree maps essentially, each of these rectangles shows you, represents the size of an item, and the items there classified hierarchically in a tree. So here this is the stock market, here you have all the companies that are in healthcare, here you have all the financial companies, here you have all the technology companies, and so on. In this case, they have the size means the market valuation, the color means the relative change over time compared to a previous time step. Based on this technique, Hive really does this partitioning very dynamically. So it's about transforming multidimensional data into a hierarchy, and you can actually define how you split it up into a hierarchy, and you can reconfigure this partition space. We have talked about tree maps, and so each rectangle is a partition subset, and then you have these nested graphics that give you summaries based on the size, shape, and color. So it's easier if I give you an example. You have London properties, so this is just a table of properties in London that are for sale. So you have, on the top level, you have the partitioning attributes, and these are dynamically defined. So house type, so you can see the top level division here is it a flat, a semi-detached house, or a terrace house. Then the next level is neighborhood. So you can see this is Brenton, this is Ealing, and so on. Of course, Brenton will again occur over here because the top level division has already is based on house type. And then within the order is defined by sale type. The visual encoding attributes here is the average price in color and the number of sales in size. In this case now we have partitioned it differently. So we have partitioned it first by neighborhood location, then by neighborhood, then by house type, then by sale time, and then by sale time over month. And we have encoded again average price by color, and we didn't use size. So size is uniform. And so what we can see here is expensive neighborhoods are near the center of the city. There is, of course,
this video accompanies the Interface 2009 paper of the same name. It demonstrates how hierarchical layouts can be used to explore multivariate data through the reconfiguration, using London property transactions as an example. We run through all the figures in the paper using the notation device temporal trends difficult to detect.
So this is the grammar that developed to define that.
This view more clearly shows the upward trend in average price. To increase the temporal granularity, we will add none to the hierarchy. We also recolor to reflect the number of sales,
So we don't have a lot of time.
Within each
Skipping
year.
forward.
As such, monthly trends by year are emphasized. To investigate the trend over the whole period, we will order all 108 months chronologically from January 2000 in the top left to December 2008 in the bottom right. This shows the rise in average prices over the period and the fall at the end. We will now assume there is no seasonal variation in sales and colour by the deviation from this baseline. We will now do the same for average price. Brown shows higher than average prices towards the end of the year, within the year. This is consistent with our findings of variation.
And then you can do also spatial positioning.
Geographical distortion. Here, rather than using boroughs, we have gridded the data into grid squares of each aggregation.
Okay. So this is a really impressive technique. If you have the chance, take a look at the whole video. I'm just going to skip the last 5 slides. Take a look at them. But I guess I covered the most important things. Yeah, this was a lot of stuff, a lot of slides today. It's going to be more relaxed in the future, but I really wanted to cover this before the fall break. And I won't be able to talk on Tuesday because Aaron is speaking, and then we have the exam on Thursday. So if you have any questions about the exam or any questions about the homework or projects or so on, I have office hours now. Some of you already have set up appointments with me to talk about the projects. If you haven't and you want to, you're welcome to. And see you guys on Tuesday.